Good evening, everyone.
Good evening, sir.
Good evening, sir.
Good evening, sir.
So, what we were discussing in the last class? So, yeah, where we were last class. Nobody is giving, nobody is understanding, or what?
No, sir, I couldn't join last live session. So
And those who joined, what about them?
Sir, we discussed about we discussed a couple of questions, and last one was on fluorescent microscopy. I think excitation, emission, microit mirror. Um, uh, Sir, we have to discuss if we have time today. Can we discuss the problem? At
Okay,
least one problem.
okay, sure. So, is it regarding your previous assignment? Or,
Yes, assignment one. I think yes, assignment one.
okay, sure. So, I also have to discuss some more concepts because actually I was going very slow because it was starting to lectures, and since the students are from different backgrounds, so I have to take everyone slowly so that they can also be able to understand the concepts. But slowly I'll be mm, um speeding up, and we'll try to move more fast and fast so that we can grab some new more concepts as well as some more problems. So let me just see that what I have collected for this week. Okay. Yeah, so for this week I have some good concepts. Hope that will be very interesting to understand. And till now we were discussing more about this microscopy, and this week also we will be discussing some about some microscopy, as well as we'll be moving towards the electron microscopy and what are the sources that we are using, and how they are working, what are the working principles and all. So this class would be very interesting, would be going to be very interesting. So please be attentive in class, and try to focus on the concepts. So I hope that my slide is visible.
Yes.
Yeah, visible.
Okay, fine. So so those who have joined, I think, first class. So yeah. So how many of you have watched the lectures, or did you get some knowledge that what we are going to do, what we are going to do in this class? How many people have watched? Sincerely, is the session started? Yes. So how many people have watched the lectures? Or nobody have watched?
So only 2,
Okay.
3 not completed.
Okay, it's fine. So how many have watched 2 lectures? Okay. So are you guys, after my class for your assignments, uh, do you guys watch lectures completely or not, or just you are depending on this problem tutorial sessions? So I would encourage you to please watch whole lectures. And one good thing I would like to tell you that when you take this lectures by your NPTEL course, please try to make some short notes, or even though if you have full time or sufficient time, then it would be always suggestible to make a good notes. It will take only once, and that notes will be for the lifetime, you know. So it's always advisable to make your note that you would be able to understand. I know that it will take some time, but if you want to know more about subjects, and if you will be working in this particular field, then it is always be advisable to have a particular notes. Then you don't, because after this session, what will happen after 4 or 5 months, you will again be stopped. You don't again go to login and all and see the lectures and all. You will have your own notes, and that would be sufficient to recall your concepts, and whatever the assignments problem, just note it down, and note that down, as well as make your own notes. Sometimes, even though if somebody's are from working or not very free, then they can make at least a short notes. Okay, so that it would be useful for you and beneficial for you for the future. Otherwise, there would be no any use of this course, because after some times it happens that we start forgetting the concepts and all. So it's good to have notes. So how many of you are making some notes or some short notes kind of a thing? Or you're just listening the lectures and solving the assignment, submitting, and that's it? Are you guys preparing notes or what? Okay. Okay, that's very nice if you are making a long notes. It will take time. I mean, suppose if you could not watch all the 5 lectures in a one go, then it's always just I will suggest you to, at least try to complete the lectures in 2 goes. If you can't do in a one go, at least try to. But your sitting time should be a long, so that you can correlate the concept. And if you are making a notes like a YouTube or the Netflix and just chilling, like writing 10 minutes, and then you are watching something else, then it won't be of any use. So just try to be attentive during your notes preparation. Try to cover it in a one go. If you can't do in a one go, then it would be a two, or not more than three. Okay, so that would be a good advice. Advice from my side, because I have done the same thing for my courses. Yes, yes, it will take time, and that's why I understand that many of you, if you're making a note, then it will take long time. So that's why I know that how much effort and time it takes actually. But if you are doing it sincerely without breaking your rhythm, okay, suppose if you are making notes in a one or two go, some people do that. Even in fact, I have done this because I try to concentrate, and I don't want to disturb myself, so that I should not break the concepts. It would be always good to make proper notes, and don't break your sitting time while taking a notes, so that you can be able to make more good notes in a less time. Okay. So for half an hour, it takes at least 2 hours to go. Yes, that's what I'm saying, Shalis. It will take time, and it will definitely take your time. But see, this is how, if you really wanted to learn these subjects, then it would be always good, because that your 2 hours notes or your 2 hours of effort would be for your lifetime. If you further want to, suppose if you will be teaching these subjects in somewhere or sometimes in your future, then that notes will always be helpful for you. Okay, so from my side, it is recommended to all of you, those who are not making, at least if you can't, if you don't have that much time to make for making a long notes, at least make some short notes, that you don't need to go. Suppose if you're preparing for any competitions exam or any written exams, and definitely the characterization subjects is one of the most important subjects that would be going to ask for every this thing, or your examination, written examination, in fact for the interview. So that time your this notes or your this effort would be very helpful to clear those tests as well as your interview. Okay, so that's what from my side, because it's just a two class. So I thought that if you people are not so much attentive in the class, because what I saw your response is not so good, that people are not very attentive, it seems. But please try to make a notes, and be try to be attentive in class. And if you can't be regular in the class, I am uploading a YouTube this lectures on YouTube also. You can watch from there also if you could not now. So yeah, again, let's start our week three session. So uh, good evening everyone, welcome to the NPTEL course of techniques of material characterizations. And this is our week 3, and we are going to deal with some doubt and problems which is covered in your week 3 module. So let's begin with our new concepts and new problems. So I'm directly going to the first problem. Okay, so the role of the outermost shell, which is also called the valence shell. Okay, so the question is about the role of outermost shell electrons in an electron microscope. Okay, so till now we were discussing mainly about the light microscopy, and slowly we are also this in this classes also we have some question about the light microscopy. But this is the transitions from where we are slowly moving towards the electron microscopy. So the very first question is from the electron microscope itself. So I do not know that many of you have not watched the lectures, and you guys are from different background. I don't know how I'm going to. Okay, so let me just take my quickly my pen, because I think I will need pen or pencil in this class, because it seems that if you have not watched the lectures, then okay. Yeah. So can, if those who have watched or those who knows about this electron microscopy, can you tell me about this. The role of the, what is the role of the this valence electron in an electron microscopy? Is detection, signal generation, electron beam production, both detection, signal generation and electron beam production, and the no role. So people are saying A, electron beam production, detection, signal generation. Okay, so those who are not from the metallurgical or the, I think it's a very basic chemistry, maybe in your plus one, sorry, in your 11th or 12th, you must have studied this. So I will not focus. You must be knowing about, what is the, so this is your like valence. What is valence? Suppose this is your like nuclear. Sorry. So this is your nucleus. So this is your like a cells. Okay. Sorry, my pen is not working. So this is your cells. Okay, let me just draw. This is your nucleus and this is your cells. Okay. So this is like your K, L, M, N. Okay, so these are your cells. So what it is asking, that the role of outermost cell. So this is your, suppose this is your outermost cell, okay, or we call it with a valency cell. So here your electron will be present. Okay, so what is the role of this electron? Whether it is used for the detection, signal generation, or the electron beam production, or both detection, signal generation and the electron beam production. Okay, so let's see and let's discuss. Okay, so here it is saying about that inner cell electrons. Okay, so this is suppose your nucleus and these are your cells. Okay, this is your inner cells, this is your, and this is your valence cells, or we should say the outer cells. This is your core cell, or we also call this the inner cells, and this is your outermost cell, or in the outermost cell we also call this a valence cell. Okay, so this valence cells electron participates in this process because it is outermost and it is easy to get off from the cells. So the inner cell electrons have a lowest energy. Okay, these electrons will have a low energy nearest to nucleus. Usually what I just in the previous cells I said that K, L, M, N. So usually K or L cells we call this the inner cells, and this is sharply defined energy, localized also. Okay, localized means it is like a, it can't be delocalized. Delocalized means it cannot be moved very fastly or the very rapidly. It requires a very high energy to, to get the electron from these cells. Okay, while the outer cell electrons, so this is your outer cells, usually your M or N cells are outer cells. So this is high energy, lowest binding energy. Okay, this is the high energy electron, but it has a lowest binding energy. Okay, and this electron is having a high binding energy. Since the outer shell electron is having a lowest binding energy, it is easy to move out from that cells as compared to inner cells electron, because that the binding energy is very high. Understood? So the outermost occupied cells. Now the conduction band. So if you know about the, if you have a little bit understanding about the semiconductor, then it's fine. I will tell you conduction band. So this is like when you study. So there would be your conduction band. So this is your conduction band. Here will be your valence band. Okay, so the conduction band here, shared electrons, range of possible energies. What is conduction band? And delocalized. So here the electron will be your delocalized in the conduction band, and this conduction band electron will only participate in that process. Okay, so the electron goes from the valence band to the conduction band, and these electrons will then move. Now the outer electrons are fairly readily detached from their atom since only small. Okay, so just now I have discussed, so the outer electrons are fairly readily detached. Okay, why? Because these atoms, since a very small amount of energy is needed to get out from there. Okay, because it is very low binded energy, so you don't need a high amount of energy, it requires a very low. It is easy availability and low mass which makes free electrons so useful. That's why we call it free electron. So in conduction band you will be having a free electron, okay, that will move and that will participate in conduction. So this is your structure, and this is your conduction band, and this is your valence cells, and this is your core cells. So when the electron goes from the valence cells to the conduction, okay, then only this electron will get participate. So this is again something related to your decay time, that it requires, we will give the energy to this electron will gain energy and will go to the conduction band, and when while coming from the conduction band to the valence band, it will release the energy. So again we will discuss, but from now it is only saying about the outer and the valence electron. Okay, so in the electron source gun, of many ways of encouraging electrons to leave a solid so that they may be accelerated towards the specimen to have proved particularly useful in the construction of electron guns. Okay, so this is your electron guns. It acts as an electron source, and from here it is, and from here it is the electron produces from this electron gun. So the most widespread system use thermodynamic emission. So we have two types of thermodynamic emission, and the another one is a field emission. So thermodynamic emission uses your from heated filament. Here we apply a heat, and from the thermodynamic emission we get electron. So temperature in excess of 2700 Kelvin. Here we require a very high temperature. Okay, this 2700 Kelvin, and we use a tungsten wire which emits an abundance of both light as well as electrons. So this is thermodynamic emissions. Now in a light bulb only light is used, but in an electron gun, electrons are accelerated across a potential difference of tens or hundreds of kilovolts. Here we apply a volts in a voltage in a range of kilovolts to generate a beam of electrons of controlled energy and hence of known wavelength. Okay, so this is the electron beam production. Do you know about this? What I'm saying about this? So the main of this concept of this question is why we use this, because we wanted to produce the electron. So that's why the role of this outermost electron in electron microscopy is to electron beam production only. And why this outermost cell? Because it is easy to produce an electron. So, it is easy to produce an electron from the outermost cell as compared to the innermost cells. And how we do that? We apply the heat, and that heat will provide an energy to an electron to move to the conduction band. Okay, so here this is your energy from your valence band, it will go so here this is also the inner cell, this is the valence cells, it will get the energy, and this electron will go to the conduction band. And here by the use or the virtue of this your heating, because here we are using a thermodynamic emission, when we apply the voltage the heat will generate, and in this way the electron will get produced from the outermost cells. So this is very simple, and I hope it is very much clear to you all. I have given you the enough explanation. Now tell me if you have any doubt on this. Is it clear? No?
Yes, sir, it is clear.
Okay. What about others? Please respond. Okay, fine.
Clear, sir.
Okay, yeah. So let's go ahead and this question I will take later. I have the more concepts about this. Slowly we'll go. But before that, I'll take this question. Huh. Okay. So what is the significance of using single crystal of lanthanum boride LaB6 instead of polycrystalline LaB6 as a thermoionic source in electron microscopy? So just now, like we have discussed, like in electron microscopy we use a thermoionic source. So here they are saying that why we are using this single crystal lanthanum boride as compared to the polycrystal, to avoid the creep, to increase the creep and the energy spread, to increase the energy spread, and there is no such advantage. So first of all, do you know the single crystal or the polycrystal? Detection is from reflected or BSC. So Arjun, the answer of your question is we use this mode. This is not detection is something else. Okay, so here it is asking about the role of your outer shell electron. Okay, so that is just the electron beam production. But what you're asking is your BSC, and I think it's not reflected. It's a scanning. So that we will come further when we will move ahead. Okay. Okay. So do you know what is single crystal, what is polycrystal? Basic material science. Yes or no? See, what is first is your single crystal. Okay, suppose this is your material and these all your suppose if you have any metals and all your grains are oriented in a single direction. You are this. It's like a single crystal. Here you won't have a grain boundary and all kind of a thing. And in polycrystal, you will have a different orientation. Arrangements are, some are oriented in this direction, some are in this direction, some are in this direction, some are in this, like this. It's many different orientations. Okay, so these are like single crystal, the polycrystals. Okay, so see how in a picture, this is a pictorial image, and this is I think a real image of that, how it looks actually. So this tip you're seeing is, it seems a very high in size, but it's very uh, small in size. Okay, and this is like this cone shape, so that the electron comes from here. So the brightness can be increased by a factor of 10 from tungsten if lanthanum boride with a work function of 3 electron volt is used. Okay, so this is your given another unit. So the electron guns which use lanthanum boride are quite common on microscopy, which are used for analytical or high resolution work. Since in both of these fields a high brightness is desirable, so we don't use this tungsten because this gives the brightness increased by 10 factor. So this is your heating current flow from here to here. This is your mounting strip, and this is your crystal, single crystal LaB6 precision microflat on this crystal. And this is how they hold this carbon ferrule and carbon heater rod. And these are this is the single crystal of this, and this is given the work function of 3 electron volt, and brightness is 10 to the power 10 uh, ampere per meter square. This, and so this is like how the arrangements are there. So this is your again here you are supplying some voltage, and this is your applied voltage in kilovolt, and from here the electron is coming, and here you will have some anode plate and all that will helps to focus the electron beam actually. And this is your LAB6 crystal. Okay, so here the main thing of your single crystal, wherever your single crystal is we are using, so the main purpose of using this single crystal is to avoid the creep. Okay, so in sometimes suppose if you have heard about your aeroplanes, in aeroplanes turbines also, I forgot the exact. I think some nickel or some alloy or some we use a single crystal only, just because to avoid a creep. Now the next question is, how many of you know about the creep? That I want to know firstly. How many of you know about the creep? Okay. Can you tell something about the creep?
The time dependent deformation mechanism.
Time dependent deformation. Okay. Are you sure, or you want to add something more on this?
Normally, stress is a function. Strain is a
So how do
function
you
of
do work?
stress. Strain is a function of stress, but in addition to that, it is also a function of time. Stress is also
No, that is fine. What you are saying is a time dependent. But something you wanna say about temperature and all?
Yes, at elevated temperature, I think it is
Yes,
time-dependent deformation at
yes,
elevated temperature.
yes, exactly. So what you are saying was right. The only thing is creep is what? It's some elevated temperature, the time dependent deformation. Okay. So when we will be applied some stress, or there would be a constant, the stress will be constant. So with the time there would be deformation at that elevated temperature, and that deformation is creep. So to avoid that deformation, okay, we use single crystal. In case of polycrystalline, the creep will be high. If you want to know more about this creep and how the single and the polycrystal effect, I would suggest you to read Dieter book of mechanical metallurgy. Okay, but since it is a very for here, it is just to focus on your for what purpose it is using in the microscopy. So you have to know creep, and to know more about creep, it is just a time dependent deformation at an elevated temperature when we apply the constant stress. So this is your creep, and to avoid this we use this lanthanum boride single crystal. Okay, so this is I wrote about the creep is a type of metal deformation that occurs at a stress below the yield strength of a metal, generally at elevated temperature. Now, what should be the operational range of filament current in an electron microscopy with thermodynamic source? Greater than IC, less than IC, just below the IC, just above the I dark. So what is the operational range of filament current? Okay, there should be some range, right, to get an electron. So what should be that range in thermodynamic source? No? Greater than IC, just below IC. What about others? So yeah, the small current flows when the potential is applied. Okay, so when we apply the potential, there would be a current flowing. But before the filament current is high enough to give rise to thermoionic emission. Okay, so here it is a small current flow when the potential is applied before the filament current is high enough to give the rise to the thermodynamic emission. So this is known as the dark current. Sorry, dark current, since it flows before the filament is hot enough to emit the light. So this is a dark current. We supply a small current flow before the filament current is high enough. Okay, so this is your filament current. So before that we apply some small amount of current. So this is called the dark current. So it flows before the filament is hot enough to emit the light. As the emitted current increases, okay, so here you can see the emitted current is increasing. So does the bias voltage, and this surpasses further electron emission. Okay, and this is known as the auto bias mechanism and account for the characteristic shape of the emission curve. Now, as the current through the filament is increased, okay, here you can see the current is increasing. There is an initial rise in the emitted electron. Okay, this is your beam current, this is your filament current. So initial rise in the emitted electron beam, here you can see when the current through the filament is increased. Okay, through the filament is increased. Okay, right here it is increasing. Then there is a initial rise. This is your initial rise in the emitted electron beam current. So here the filament current is increasing. This is beam current, initial rise in the beam current. This eventually saturates. Okay, so here it is increasing. After some point of time, it is start saturating. Okay, and there is no point in passing more than the critical current through the filament, since this merely increase the temperature of the filament, thus reducing its lifetime without giving rise to any additional beam current. So when we apply a filament current, then initially the beam current also starts increasing, but after some point of time it gets saturated. Why? Because this is the critical current through the filament. Since this is merely increase the temperature, so the beam current will also saturate, and this will reduce the lifetime of your filament. Okay, understood? So here the question is here, what should be the operational range of filament current? So this is your filament current in an electron microscopy with thermodynamic source. So greater than IC. Should it be greater than IC? Less than IC? If it is less than IC, this would be there. So if suppose less than IC, this will also become. So will be generating enough beam current? No. Just below the IC, just above the I dark. So this is just below the IC, just above the I dark. So what could be the answer? Just below the IC. Do you get it? Why I'm saying? Let's suppose this is your range. So in this range, if you will operate, so
No.
in this range, when we will operate, the beam current will be low. When we go above IC, your lifetime of your filament will reduce also, and your beam current will saturate. So it's always advisable to use your filament current just below the IC so that you can get enough beam current, as well as your lifetime of your filament will also not decrease or reduce, isn't it? Okay, is it clear why it is below IC, why we are not going above IC?
Clear, sir.
Yeah, fine. Huh. So let's go to another question. Out of cold FEG and hot FEG. So this is field emission gun. FEG is what? Field emission gun. So there is two, cold and hot. Which one is better in terms of safety of specimen and the cost of an instrument? So the first thing is here, as a researcher, when you will buy any instrument, it's not something you will always focus on your purpose. Purpose is one thing, but safety is another thing. Because if the handling or the safety of your instrument is easy, the more will be chances of your instrument to run for the more longer period of a time. But if in any instrument the safety is not good, or you are not, the condition is not good, you are not taking care of an instrument, it won't run for the longer time. Okay, so this is one thing. Second thing is your cost of an instrument. Do you know, do you have any idea about how much this costs around this SCM or all? Nowadays, very advanced SCM are coming. Anyone of you, if you are college, have this SCM or something machine instrument?
1.5 to 2 crores, sir.
Yes, it's in crores. And nowadays, very advanced. Like in my institute, just recently, one instrument came, and I think it's more than 5 crore because it has inbuilt like ABHD setup also. And they have a multi-functionality. It's not just fulfilling the purpose of your SCM. I do not know because I have not used that equipment. But yeah, I heard about it. I mean, it has all the things inbuilt inside your machine. So the cost of your instrument is also required. I mean, very, very important. Now, so which one is better? Hot, cold, or both, or none of this? So, what is your opinion on this? Someone is saying hot. Hot, cold, cold. Both may not satisfy the conditions. Yeah, that's what you have to think. And if it is not satisfying, why? And if one can satisfy, then why other cannot? Yes. So this field emission currents depends very strongly on the applied field. For field in excess of about 5 into 10 is to power 9 volt per meter, the current emitted by field emission at room temperature exceeds that which can be thermoionically emitted, which is called the cold FEG. Okay, what is happening here? For a field in excess of about this voltage per meter, the current emitted by field emission at room temperature, here field emission at room temperature exceeds that which can be thermoionically emitted. So in order to apply such a high field, the emitter, usually tungsten, has to be prepared in the form of sharp point. So here you just see how sharp it is. It's like more sharper than your nib of your pen, this tip. So the diameter at the point must be of about it's zero point 0.1 micrometer. It's like you're more thinner than your hair. Just imagine, which is orders of magnitudes finer than a pin. So the emitter is a rather delicate structure. Now see how delicate this structure could be. If it just broke, then it's, I mean, it can't be repaired. You have to buy a new one. That's why you have to maintain some proper distance when you are doing sampling. Your tip should not touch the specimen. For this fine point to be preserved in use, it must be operated in an environment with very few ions, and this dictates the use of ultra high vacuum techniques. So here when we use this inside the chamber, we have to create a ultra high vacuum, okay, so that it can operate in this environment, and a very few ions, and this, you know, the electrons and the ions can travel in a particular direction. Now the vacuum in the gun must be lower than 10 is to power 7 Pascal, which is rather better and more expensive to achieve than 10 is to power minus 2 or minus 3, which is common in thermoionic guns. But here it should be maintained, lower than the 10 is to power minus 7. So the electrons are extracted from the fine tip by a first anode, and firstly it will come from the anode and then accelerated down the column by a second anode. Okay, so here this is your tip. So this is your first extraction anode or the first anode. The voltage applied few kilovolt. Now it will extract the electron, and there will be the second anode, which is the acceleration. Now this extracted electron will accelerate by this anode, and here the voltage is high, 100 kilovolt. Okay. Now, what is the advantage of FEG? An important feature of field emission sources is that the emitted electrons have very well defined energies. Since it is emitted from a very sharp tip, see the energy defines the maximum energy is at at the center, and this is your energy distribution, and this is very less. The range is point, this is like this, okay, and this is your counts, and this is your 0.35 electron volt. So whereas the electron from a thermoionic source inevitably have an energy spread of 1 to 2 electron volt, the electrons from a cold FEG have a much smaller energy spread, usually less than 0.5 electron. So this is less than 0.5. Whereas when we use a thermodynamic source, the energy spread is 1 to 2 electron volt. It is not focused, and we want a focused energy. Okay, the energy spread should be focused. Thus, for both analytical and high resolution electron microscopy, field emission source are important, okay, as compared to the thermodynamic source. not just because they provide a high brightness beam, but because they provide a clean monochromatic supply of electron. Okay, clean monochromatic, it means the energy spread won't be a very high. Okay, it's the your beam should be like very focused when it is scanning to a sample. So the electron beam energy distribution of cold FEG on this is the model of the this electron microscopy, which is from the Hitachi. Hitachi is one of the very famous Japanese company which provides various kinds of electron microscopy, high technology, measured with this Gatton electron energy loss spectroscopy detector. Okay, so here this is your cold FEG. This is the energy distribution in your cold FEG is your much smaller. So your cold FEG is good to use as compared to the hot FEG. There is a two reason behind this. The first reason is it's provide a higher brightness, and apart from the brightness, the energy dispersion or the energy spread in this is very good, and it is gives a very focused electron beam, so that it's good for a specimen to generate a signal. Now tell me, is it clear somewhat why the cold is better? With respect to cost, I do not have any idea about this cost, but about the proper. But as per the principle or the mechanism, what is there is what I got from the lectures. But yeah, I have not looked up upon the cost, and if you want further, you can just go and see because it's not very readily available that what is the cost and all. So you have to get the quotation. It's not something that is available in Google, right? And cost varies, depends on the time. If I get the quotation from now, it can vary. If I want the quotation after 2 months, again it can be vary. And again, it depends on the model to model. What kind of a model do you want to use? With respect to the question, yes, with respect to the question, definitely it is asked about the cost. So I do not have the proper figure or the exact amount, but definitely if it is mentioning the cost, then the cold FEG should be a lesser. I think so. But yeah, as a principle wise or as a mechanism wise, the cold is better as compared to the um, hotter one. Okay. Should I go ahead?
Yes, sir.
Okay. Just a second. Now I think you guys can answer this question. It's pretty simple, and just now I think from the last slides you can get some idea to to able to guess or to give the answer even if you have not watched the lecture. Yeah. So this is again about the field emission source is beneficial for high resolution electron microscopy because it provides very small energy spread and minimal spherical aberration, because it provides minimal uh, astigmatism and distortion, because it provides large focal length and short focal. So yeah, definitely provides a very small energy spread as you have already seen. And yeah, this was the answer. It was pretty simple and I hope it is very clear. So why the gap between soft iron pole pieces is generally made very small in electromagnetic lenses for electron microscopy? In order to make it work like thick lens, thin lens, electromagnetic lens, magnetic lens. Can you tell me why the soft iron pole pieces is generally made very small? So let's see. This is your electrons in electron microscopy lenses and this is your magnet. So initially the electron is unaffected, okay, when we apply a magnetic field which is parallel to its direction of travel, but experiences a small force of magnitude F, and this is F is what? This formula B into R into A for the small radial, okay. So this force causes the electron to travel in a helix along the lens. So now the electrons will travel like this, okay. As soon as it starts to spiral, it has a component of velocity v perpendicular to the plane of the paper and therefore experiences a force of magnitude this in a radial direction. The helical path follows a tighter and tighter radius. The effect is that a parallel beam of electrons entering the lens is caused to converge to a point exactly as light is focused by a glass lens. Okay, so when it is coming like this, it will try to focus. So this is your electron. Okay, it is going from here, and this is your coil. And from here, when your electron will go, so this is your soft iron pole pieces, okay. So here you can see how it is making this, okay, so that the electron entering the lens is caused to converge. Here the electron is entering and converge to the point exactly where we want to focus. Okay, so this is the main thing, and that's why we use it in order to make it work like a thin lens. Okay, so when it will be working, so the main reason is to converge your electron to mainly focus when your electron is entering from here. That's why we use this soft iron hole pieces so that it can work like a thin lenses. And I think someone is asking about some problem. So people is saying in order to make it, no, it's not the electromagnetic lenses, it's like a thin lenses. And someone was asking about me spherical aberration problem. So let me see that whether I have collected the problem regarding to that. Ah, yes, I have. Yes. So someone was asking me who was that Swaroop. Okay, yeah. Yes, so you were asking about this Swaroop, this kind of a problem?
Yes, yes, sir. Yes, yes.
Okay, yeah, fine. So yeah, I got one problem from. So it is asking about for a spherical aberration of 0.5 mm, find out the optimum resolution of an electron microscopy operating at 200 kilowatt, ignoring the So did you try or so how many of you have tried this problem? Okay, let me firstly make it full screen. Just tell me how many of you have tried to solve this problem. What about others? Please tell me. Just see the problem. And if you have not, just try to solve. I will give you few minutes to solve this. And even though if you cannot, at least just try to attempt this. Then I'll give you the hint. Okay, I will give you the hint and just now try to solve this. Please just see the questions, what it has given, or just note it down the question, and this is the hint, and just try to solve this. So did you get it or something? No, you didn't try this, or should I give you the hint? So I think so. This can be, I will give you the hint and just you do the calculation by yourself and I'll give you the hint. Okay. So because since nobody is solving and I'm, I'll just give you and okay. Just let me take another slide. And just try in this way by yourself and in the next class I will ask everyone that whether they have solved it or not, because since I want you people to get it solved and let me know, because at least you try by yourself. Okay. So I'll give you, try to give you, since the resolution formula is 0.61 into lambda by Na. Okay, lambda is the wavelength, N is the numerical aperture. So here the operating at 200 kilowatt it is giving. Okay, so how you will calculate this lambda? You will calculate this 150 by root of V. Now, since the accelerating voltage is kilovolt, so here you will get the value of lambda. Now you put this for electron microscope, you have to see the numerical aperture. You just have to search, it should be mentioned somewhere, and then put that value 0.61 and whatever this lambda is calculated and the numerical aperture for the electron microscopy, and then here you will get some answer which is your resolution. I hope this is sufficient hint. And
But what is beta or alpha? That is not given.
where
Numerical aperture I can come to know if I know beta or alpha, I mean, sin alpha or sin beta.
so what you want to know?
Beta
Beta is angle, but it is not giving here, no?
is not given.
Yeah. So you just try solving by this approach. Maybe because the beta is not given, since I am feeling that this could be one like what we have studied in our past classes. So just try solving by this method, and if you cannot get, then I'll try to solve it by some other formula, and I try to get it from there.
See, this numerical aperture formula doesn't consider aberrations at all.
But here, since the beta has not given, right?
No,
So
otherwise also numerical aperture, whatever formula you've written, lambda equals to 0.61 lambda,
yes, yes, yes,
that doesn't consider aberration part of it.
yes. So I think this would be okay if you just try to, or yeah, I think because beta has not given in this question, or it should be something. I mean, I'm not sure because something is missing in this question. I am feeling so. I don't know why. I think you just try to correlate numerical aperture with the spherical aberration. Just let me check. Um you just try by using this formula, whatever. Try solving this. Just I have found this formula from somewhere. You are this spherical aberration equals to 1/4 of lambda upon numerical aperture square. So yeah, from here if you can find something, because the spherical aberration is given, and the lambda you can find by the voltage, and then you just try to solve this and hope you will be able to get right.
Can you tell the answer so that we can cross check?
Huh?
What is the answer, right? Correct answer, if you can tell.
I have also not thought actually, because I was just giving this concept, so I could not check the answer properly, but I have to see the answers in the assignments. I was just collecting the questions, but let me, I will check in the assignment. Huh.
But here also finding Na is difficult because alpha, beta is not given.
Hmm. Okay. Uh, okay, I'll check this problem, and we'll try to solve in the next class. because something I'm getting something, but it's not the matching of this answer. Maybe some unit conversion I'll require. Okay, I'll check and will give. But you can just try by just maybe I'm mistaking in this what to say this unit conversion. But you just calculate this spherical aberration from this formula. The spherical aberration is given. Numerical aperture you can get it from here, and the lambda is 150 by root of v. V voltage is given, and this is the resolution formula 0.61 lambda upon numerical aperture. So numerical aperture you can get it from here, and lambda you can get it from this formula. And just try to put and get and see what you are getting. Okay.
Okay, sir.
Oh yeah. Now the electron microscope provides what? Imaging. It is very simple. Imaging diffraction, diffraction spectroscopy, imaging spectroscopy, or all. It's just very basics and simple. Any guesses? B. Yes. So actually, this is regarding the importance that why we use this. So the electron microscopy is not just a single technique, but a diversity of different ones that offer unique possibilities to gain insight into. You can find the structure, you can find the topology, you can find the morphology, you can find the composition of material. Okay, so here various imaging and spectroscopic methods are represent in indispensable tool for the characterization of all kind of specimen on increasingly smaller size scale with the ultimate limit of single atom. To observe specimen include inorganic, organic, micro nanostructures, minerals, biological specimens. The wealth of very different information that is obtainable by various methods is caused by the multitude of signals that arise when an electron interacts with specimen. Okay, so we will see that how electron is specimen, and we will get a different information from there, from the different depth. Since the gaining a basic understanding of this interaction is an essential, the different types of electron interaction are basis of most electron microscopy. So we will get all kind of information. So we can get the imaging, we can get diffraction, we can get a spectroscopy. So imaging is for what? We can get the surface topology, morphology. Diffraction, we can get the crystal structure, about the crystal orientation. Spectroscopy, we can get the compositional analysis or the elemental analysis. So yeah, this kind of a what to say information we can get from STM. So this is how your typical STM instrument it looks like. Okay, I think this is TM. I'm not sure, but this is for sure STM. So yeah, this was a very simple question. So preferred mode of electron material interaction in TM and STM or what? What is the preferred mode? Which one is more preferred? Someone is saying option B and one is saying D. So do you know first of all what is elastic, inelastic? So elastic is what? Elastic interaction or scattering is defined as the process which, although it might change the direction of the primary electron, does not change its energy dictably. Okay, so it will change the direction, but the energy will be your conserved. It won't change the energy. The electrons are scattered from electron cloud and nucleus of a single atom at angle theta. So suppose your electron is coming, okay, and then it will move. It won't lose its energy by interacting with the other nucleus or other electron. So this type of scattering results from Coulombic interaction, which is involving electrostatic charges between the primary electron and both the nucleus and the electron around it. This is known as Rutherford scattering, which is plus one thing. And elastic is important in electron microscopy because it is a measure mechanism by which electrons are defined, and also because elastically scattered electrons are the main contributors of the so it is very simple. It's just electron is going, it is without interacting, it is getting it revert back, and it do not interact with any atoms, so the energy will be your constant. Now in the inelastic, it's like this. So suppose your incident electron is coming due to the effect of your this nucleus. It won't revert back like your this electron. This is your elastic scattering. It can deviate from its path. So this is your inelastic electrons. Okay, this is your scattered electron. So this is your inelastic interaction. So electron penetrating into the electron cloud of an atom is interacted by positive potential by a nucleus, and its path is deflected towards the core. Okay, so this is the inelastic interaction. So in the inelastic interaction, the energy of the incident electron is transferred to the sample of atoms because it will interact with the atoms. In the case of elastic, it won't interact. It will come and go back. After interaction, electron energy is reduced. The energy is getting reduced. Why? Because it has given the energy because it interacted with the other atoms. Now, the energy transferred to the specimen can cause different signals, such as since the energy is interacted with the specimen, now the different signals will generate, such as X-ray, auxiliary electron, secondary electron, plasmons, phonons, UV quanta, cathodoluminescence. So these are all some signals which we get from the result of inelastic scattering. Okay, is it clear? Now, signals caused by inelastic electron matter interactions are predominantly utilized in the methods of analytical electron microscopy in scanning electron microscopy. So it is mainly, used for the analytical detection. Most of this energy of electron beam will eventually end up heating the sample, which is why, because the phonon excitation of the atomic lattice. Okay, when some atom will come and hit your samples, then there will be a Conovan excitation will coming, and there will be a vibration in the atomic lattice. So that's why your specimen will get heated. Now, before the electron comes to rest, they undergo two types of scattering, coherent and the incoherent. This is further part. But since this is about the inelastic and the elastic, so the question was preferred mode for electron material interaction. Okay, so it was elastic and inelastic respectively. Why? Because it has a different importance. It has a different importance. Because from the elastic we get a different information. From inelastic we will get a different information. So both are very important for us. Is it clear that elastic and inelastic, how it works? How it works and why we use this and what is exactly happening? Can you show the question? Okay. This is the question. So TM elastic and SCM inelastic. No, it's not like that. It's saying that, yeah. So preferred mode of electron material interaction in TM and SCM are what? So it is asking in TM and SCM. So for that you have to know which one is elastic and which one what is inelastic. So in case of TM, yes, you are right. It is elastic, and in case of SCM, it is inelastic. So now my question is it clear that why elastic for TM and why inelastic for SCM? Is it clear that why we need inelastic for SCM? Since we use SCM not just for the in TM, actually it has to be inelastic because that electron is passing. So if electron will interact with the other atoms, it will deviate from its path and it cannot transmit through your samples. Basic principle of TM is what? Transmitted electron microscopy. So if your electron will deviate from its path, it cannot reach to the detector, or it cannot go through the samples. But in case of SCM, your electron is coming, interacting with your specimen, depends on the depth from where your signals or your electron is interacting. Different kind of signals is generated, such as your Auger electron, secondary electron, your X-ray, your plasmons, phonons, cathodoluminescence, X-ray, depends on that, right? So here this is your incident electron beam is coming from, this is this depth, your Auger electron will come. If you further increase the depth from here, secondary electron will come. Further, if you will increase, your backscattered electron will come. Further, again depth, your X-ray will come, and it lasts from cathodoluminescence. So these are the signals which you will get from a different thickness that we will see further. So this question is again, elastic interaction by atom, heavily charged nucleus will lead to inelastic, low scattering angle, high scattering angle, exponential, or no change. So here you just see inelastic, it is very high angle. It's like a theta, but it's completely reverting back. Okay, elastic interaction deflects the electron beam along new trajectory, causing them to spread laterally. So this is back scattering. Back scattering means what? It's coming and going back, called back scattered electron. Okay, so here this is defined the amplitude of scattering from the atom divided by the amplitude of scattering. So yeah, the main thing is this provides the information of the class of information of SEM imaging. Okay, and here the strength of scattering by electron by an atom depends on its atomic number and described in terms of it. So basically here it is a very high angle, as you can see. Just see, this is inelastic. This angle is high or this angle is high. Obviously now this is completely rotating revert back. So it's a very high scattering angle, elastic interaction. Okay. Now, which of these parameters describes the chance of scattering of an electron? Mean free path, interaction, cross section, both, or the thickness variable? Tell me. So yeah, so the scattering of an electron is, this is like a cross section. So electron passes within this area, the interaction will certainly occur. Okay, so when the electron will pass through certain cross section, definitely scattering will occur. So the cross section is expressed in the area which the scattering particle appears to present to the electron. So definitely, suppose there is n particle per unit volume of the specimen, and the cross section particular scattering event is sigma. The probability of a single electron being scattered in this passes through thickness of dx of the specimen. So this is your n number of particles, this is thickness, and this is your scattering event. So this is through the cross section interaction. So this is total interaction will be your, some are go through the inelastic, some are through the elastic. So this is total is the sum of inelastic and the elastic. So this is also because of the cross section that when you see the lectures you will get to know. And also the mean free path. Mean free path is what? The average distance traveled by electron between two scattering events. Suppose the electron is firstly it interact with atom, then the further interaction with another atom. So it will, how much distance it will move. So when the electron kinetic energy is increasing, so you can see how the mean free path is changing. So definitely mean free path also affects the scattering. So the answer is a cross section also and the mean free path. Both affects the scattering event. So I hope that it is clear. And now in the next class, I'll be discussing this, how this electron signals and by what depth, what kind of signals generates this. So I'll be taking this, and this is very good. And from here, your main SCM scanning electron microscopy will start. Okay. So I hope it is clear a little bit, and we'll also try to solve some problems. And yeah, so that's all for today's. And uh, remaining portion we'll take in the next class. Thank you and goodbye.
Thank you, sir. Good night.